All right, welcome back to the fundamentals of IPOS. We are moving into part 4 of learning the IPOS programming language, and this, of course, is session 7. So we are really making good progress. Hope you're appreciating the progress that you're making and getting a greater grip on IPOS. So let's learn something new. Today we're going to spend some time looking at the built-in functions in the IPOS library. We've talked about functions a little bit. Now we're going to get into them in much greater depth. I'm going to explain what they are, how they work, and we'll go over some of the built-in functions in the IPOS library that you will use frequently. So let's start with the built-in functions. What is a function? As I've said before, it's just a named block of code that performs a specific job or operation. Programs use functions to do specific tasks. They're really a way of organizing your program and making it a little more structured. So functions make your programs more organized, more efficient, and easier to debug. Instead of viewing the program as just a big mass of code, you view it as smaller blocks of code and you work on them individually until you get them working right. So that's one very definite advantage of functions. Also, functions let you reuse code. If you write a really brilliant function to do some kind of operation, you can just cut and paste it into other programs that you write, and you don't have to debug it or anything. You've got a good piece of code ready to go. Now, as you know, all programs have at least one function, the main function. That's the outer function for task 1's code. Most programs have far more functions than just main, but that's one you're familiar with at this point. IPOS includes a useful function library. It contains 32 predefined functions that do a wide variety of things. We'll look at those in just a couple minutes. And of course, you can create your own custom functions to do whatever you'd like. And as you gain experience as a programmer, you will certainly be doing that. All functions have a name and possibly a set of what are called input parameters. Let's look at an example. This is one of the built-in functions. It's called _go0. It's used to reference the VFD, and it's got both of these features. The name is _go0, and type is a single parameter. Parameters are in parentheses. There's more than one parameter. There will be a list separated by commas. In this case, there's just one. The parameter customizes the function's behavior. You provide the parameter, and that tells that function how to behave. In this case, it's a referencing function, so that modifies how referencing takes place. We call functions, that means activate them so they do their thing, by using their name, and we supply any parameters that are required in parentheses. So for example, with go0, we might say go0 and then give it an 8. And 8 would tell it to modify its behavior in a particular way. So it's kind of like this. It's like you throw the 8 into the meat grinder, and then calling the name go0 is turning the handle, and then the function does its thing. So that's kind of the metaphor here. Hopefully that made sense. That's how functions work. I will mention just parenthetically that not all functions have parameters, but many of them do. And don't forget, function calls end in a semicolon, so this is definitely a place you need a semicolon. All right, IPOS has 32 built-in predefined functions, and here they are. They're divided into different categories. Some support communications, either within the VFD or between multiple VFDs. There's unit control, which does various things with the VFD. There's program management, which handles things like the task system and delays and so forth. There are functions for configuring the system, for positioning, and for bit manipulation. So there are lots of different functions, and they do all kinds of handy things. All built-in functions begin with an underscore. That's just so you can kind of recognize them as built in. And their parameter aliases are defined in constant b.h. So while you could certainly just pass them numbers to configure them, a lot of their parameters have been given meaningful names in constant b.h. These are aliases. That's, again, it just makes your program easier, more readable. And all this is documented on pages 205 through 245 in the IPOS manual. A very easy way to insert one of the built-in functions is to hit Control-T when you're in the IPOS editor. That pops up a list of the functions, and then there are drop-down boxes where you can pick parameters and various other things. For example, here, if you hit Control-T and you want to use axis stop, you can click that. Then you can pick the parameters that are available, and those are the aliases. And then when you're all done, you just click the Add button and it inserts it into your code. Here's another function, bitClear. This one takes numeric parameters, so it shows you the available choices from a list. And again, you just click Add, and there you go. All right, let's look at a few of the built-in functions. We'll start with this one. You've actually seen it before. It is wait, and it just causes a delay for a specific amount of time. Time is a constant. It is specified in milliseconds. That's 1/1000th of a second. So for example, 100 milliseconds would be a tenth of a second. So you can either just put a number there, or you can put in a program constant that is set to a number. And the code will delay when it encounters this and then resume execution when the wait time is over. So it just pauses execution. It doesn't affect the other tasks. It only affects the task you're in, so don't worry about messing anything else up if you're running more than one task at a time. All right, here's a handy one, the input function, wait input. This takes two parameters, and what it does, it waits until specific inputs are at a specific level. So you could, for example, use the digital inputs to make something happen. And what wait input will do is it will just sit and camp out on those until they're at the level you specify, and then it will continue to the line after it. So this basically hangs your code until the inputs are what you want. Now let's see how these two parameters configure its behavior. First of all, level is the logic level, either 0 or 1, that the inputs must be to end the wait. So you would have to specify a 0 or 1 here to indicate what you're waiting on. And then secondly, you give it a mask telling which bits of the different inputs to monitor and which ones to ignore. So this would be a binary number. If you want to ignore a bit, just put a 0 in its position. If you want to monitor it, put a 1. And here's just a little side note. I have no idea why this is true. It's just a fact of life in IPOS. DI06 and DI07 can't be monitored for some reason. No idea why. So these are the bits you can monitor, and this is the order that they would be in the mask. So the mask has a total of 14 bits down at the lower end, the least significant bit end. So if you want to monitor a bit, put a 1 in that position. If you don't, put a 0. There are some bit manipulation functions. Now, as you know, you can manipulate bits using some of the bitwise operations we learned about in our last section. But these are functions that do those things maybe a little easier. Here's a nice one, bitClear. It clears a specific bit in a variable. So you pass it any variable, any H variable, or its name if you're using a named variable, and then just a number which says which bit you want to clear. So it's a constant identifying the bit number. Remember, bit numbers start with 0 and end with 31, so a number between 0 and 31. And it will clear that bit. There's also bit set, which does exactly the same thing and works in exactly the same way, except instead of clearing the bit, it sets it. So send it a variable and then a number from 0 to 31, and it will change that specific bit. And then this is kind of a novel one, bit move. It copies a specific bit from one variable into another. So notice there that we have two variables, which I call hx and hy. These are just any two h variables. So hx X is the destination, that's where the copy goes into, and HY is the source, where it comes from. And here's something you should be aware of. You can use the same variable for both. In other words, you can copy a bit from one location in a variable somewhere else in the same variable. So if you want to do that, that's perfectly legal. You can just use the same variable name. And bit 1 and bit 2 identify the bit number in each variable. So that will indicate where it comes from in the source, where it's going to in the destination. And again, bit numbers start with 0 and end with 31. So useful little tool. Bit move negative does exactly the same thing. It works in exactly the same way. But when it's copying the bit, it also inverts it or flips it to the opposite state. That can be useful in certain situations. Okay, so you've just learned a handful of very useful functions. I think it's time to write a program. So we're going to create a brand new program, program 4, so you'll have to switch source files. And here are the things I'd like you to do. Of course, create your new program called program 4, and just again a reminder, don't forget, update your comments and your header information every time you do this. It's a good habit. And here's what your program does. First of all, turn off all the lights attached to DO10 through DO17. Then use the wait input function to watch DI10, and you want to watch until it is turned on and then off. So you're going to have to check for two conditions, it being switched on and then being switched off. So you're going to toggle that switch on-off to make things start. As soon as that happens, turn on all the lights attached to DO10 through DO17 and keep them on for 1 second, 1,000 milliseconds. Then turn on every other light attached to DO10 through DO17 for 1 second. Then reverse that pattern of lights on DO10 through DO17 for 1 second. Turn on all the lights attached to DO10 through DO17 for 1 second, then turn them off. And then finally, I'm telling you here specifically to use a function. The other ones you can use whatever technique you prefer, but for this one I want you to use bit move negative to turn the DO10 light on, then off, then on at second intervals. So it's going to blink on, off, on at second intervals. And then let the code loop back to the beginning where it turns off all the lights and starts waiting again. So it'll be waiting, and then if you flip DI10 again, it'll go through another cycle. Okay, hope that made sense. Use whatever techniques or functions you like. Here's a helpful hint for you. There are two system variables which will help you to solve this task. They are H480 and H521. They go by the name opt-outp IPOS and outp level B. They will definitely help you in solving this problem. Pause the video, go do it. Then when you're done, come on back and I'll show you how I solved it. Okay, well, hope you got it working. Let's take a look at my code, and you can compare it to how you approach the problem. This is the first of a number of programs we're going to be writing that will be doing some blinking lights. As I told you a few sessions ago, we have limited user interface on a Movi Drive B, so blinking the lights is really all we can do in these early stages. But this will give us a chance to work with the I/O system and also use some of the functions we've just learned. So as you can see, I've already changed my source program to program 4, which is a brand new one. I've updated my header appropriately, and I've cleaned out all the code from the previous program, which we're not going to reuse, so we just have our basic skeleton here. Now, remember, we're going to be doing a number of different things with the lights. According to our instructions, the very first thing we have to do is just turn all the lights off that are attached to DO10 through DO17. We're using the outputs on our I/O expansion card, not the built-in ones. Remember, we've set all these to IPOS outputs, so we should be able to manipulate them easily. There are two ways you can control these. One is to write to the H variable 480, which happens to be the system variable associated with the option card output. But a better thing to do would be to call it by name instead of having to look up its H number. And if you look in the IPOS manual, it will tell you that the alias that's been defined for it in constant b.h is opt-outp IPOS. And I pointed this out to you a number of times as we've gone along. So the very first thing we're going to do is just set it to 0, and that will turn off all the lights associated with it. Remember, the bottom 8 bits on that number control the outputs. So I'm just going to put this line of code in. So that will turn off all the lights. The next thing we have to do is watch digital input 10. And we're going to look for it to be toggled from the off to the on and the off condition. So we're going to use one of those built-in functions. We're going to use wait input to wait for it to be turned on, and then we'll wait for it to be turned off. So we're actually going to use 2 wait inputs. So let me go ahead and insert the code for that, and then I'll explain how they work. Okay, remember, wait input takes 2 parameters. The first is a number, either a 1 or a 0, indicating what we're waiting for. So in this case, we're waiting for that switch to go to the on condition. So we're going to use 1 in our first wait input, and then we're waiting for it to go off again. So we'll use 0 in our second. And then the second parameter is simply which bits we wish to watch. So we're going to watch just one bit, DI10, and that happens to be the 7th bit. Because remember, wait input looks at all the digital inputs, both the built-in ones and the option card, but it doesn't look at DI6 and DI7. So that means DI10 is actually going to be the 7th bit that it is watching for. So notice I've used binary numbers here. When you're working with individual bits, it's often easier to use binary numbers. Remember, we put a 0B in front of them and then just ones and zeros. That's so much easier to keep track of bits, and so that's what I've done. I'm just basically looking at the DI10 bit, I'm waiting for it to go on, then I'm waiting for it to go off. Fairly simple and straightforward. All right, now the next instruction is, as soon as this switch pattern has occurred, that on to off pattern, we're to turn all the lights on. Here's what we're going to do. We're going to write a new value to opt-outp IPOS. And there we go. Notice I'm using binary. I don't have to, of course. I could use decimal or hexadecimal if I wanted. But as I said, when you're working with bits, it's often nice to use binary. So I'm just turning on the bottom 8 bits of that number. That'll turn on all 8 lights, DO 10 through 17. We're also then supposed to wait 1 second. So I'm going to use the wait function. And remember, wait takes the time in milliseconds, so I'm going to put 1,000 milliseconds in for a 1 second delay. Very simple. No need to comment that. It's obvious what wait does. Next thing I'm supposed to do is turn every other light on. So there we go. I've just put in a binary pattern with every other light on. And we're supposed to wait another 1 second. Then we're supposed to reverse the pattern. Of course, I could do it using a crafty bitwise manipulation instruction, but why bother? I'm just going to send that pattern out in reverse. So there we go. I've reversed the pattern, and of course, I can't forget to wait another 1,000 milliseconds. The next instruction is to turn all the lights on. So once again, I'm just going to write 8 ones into that, and of course can't forget to wait. Now I'm supposed to turn all the lights off again. And I don't have to wait here. So that's sort of the first part of my light show. Now, according to our instructions, I need to use the bit move negative function to turn just the DO10 light on, off, and on. In other words, I need to toggle it 3 times. It's currently off, so by toggling it once, it'll go on. Toggling it again, it'll go off. Toggling it one more time, it will go on. Remember what bit move negative does. It copies a bit from one memory location to another. And of course, bit move negative inverts the bit every time it copies it. Here's what we're going to do. Okay, what we've done is we've taken a bit move negative and we are going to be copying from OutP level B into opt OutP IPOS. Remember, opt OutP IPOS is a write-only location. In other words, you can write into it to change the status of the digital outputs, which of course would operate the light, but you can't read it to find out what its current status is, which means we can't read it and invert it with bit move negative. So what we're doing is we read OutP level B, which has the status of all the digital outputs, both the built-in and the expansion, and we copy just the bit we're interested in, which happens to be bit 6, that's DO10 in that location, and we copy it into the DO10 bit and opt OutP IPOS, which is bit 0. So we're copying from bit 6 in one into bit 0 in the other, and we're inverting it along the way. And that is what's going to cause our light to blink. Okay, so we'll do that, and I better straighten up this comment here, and don't forget that weight, 1000. And then we need to do that 2 more times, so I'm just going to copy and paste this twice, and there we go. Now that should do the job. So when we compile this and run it, we should have all our lights go off, then all our lights go on. We get every other light, the pattern reverses, all the lights go on, then they go off, and then DO10 should go on, off, on, and then finally it's going to loop back around because that's the end of the while loop, so it'll go back to the top, the lights will go off, and it'll go back to waiting for us to toggle the DI10 switch. So that's what we expect it to do. Now we need to find out if that really happens. So I'm going to go ahead and compile and load our program, and everything's fine there. So I'm going to run it, and then I'm going to go flip the switch and look at the light patterns, and I'll turn the camera on so you can see what's happening too. So here we go. Start our program, go flip the switch. All right, and as you can see, everything worked great. So hopefully your program worked as well. I hope you found that a little easier than the last program. That math program was definitely a little hefty, but this one was pretty simple when it came down to it. Okay, very good. All right, well, we've learned a bit about the built-in functions. Now let's move on and learn about something really interesting called decision structures. One of the most important features in any program is the ability to make decisions based on the contents of a variable or the value of an expression. If you can't check values and make decisions based on them, you really can't write useful programs. Think of decisions like forks in the road, where each path leads to a different destination. All the decisions come down to whether an expression evaluates to true or false. So we're going to be working with a lot of the logical mathematical operations here. We're going to just be getting that 1 and 0 outcome, and that will decide how we go down the decision path. So we're going to use a series of symbols. They're called evaluation symbols, and they determine whether an expression is true or false. And that will then determine what kind of decision we make. These are the expression evaluation symbols. Equal to, notice it's a double equal, not just 1, but 2, and there are no spaces between them. Not equal, which is an exclamation point and an equal sign, again, no space. Greater than, less than, greater than or equal to, less than or equal to. So these symbols will evaluate various variables and will give a true or false, depending upon how the evaluation turns out. You can also connect several expressions together using the logical operators. You already know about these. There's the not operator, which takes the opposite. There's and, the double ampersand, and or, the double vertical pipe. The first construction we're going to look at is called the if construction. It executes one or more lines of code if an expression evaluates to true. So let's see one. Notice the expression is in parentheses. If h1 equals 100, then execute the function go_rel. If it doesn't equal 100, it will just skip to the next line. It won't execute that line. Notice there's the semicolon after the function there, but not after the if itself. If h5 is greater than or equal to 32, go 0. If it's not greater than or equal to 32, it won't. It'll just skip to the next line. If the current position does not equal 16,384, then do an axis stop function. Otherwise, skip to the next line. And this is kind of a fun one. If not stopped, do a bit set. In other words, take stop, invert it, and if when you invert it, it's true, then do that. In other words, if stopped is false. All right, so these are simple if statements. They each execute a single line of code if the expression evaluates to true. Now, what if you need to execute more than one line of code, which happens most of the time, in fact? Guess what? Our friend the curly braces take over here and enclose our code. So here are some examples of multi-line if constructions. If h1 is greater than 100, then it's going to do two things, the code in the curly braces, go ABS and bit clear. Okay, so that's what you do if you need more than one line of code. Remember, I always said it's never wrong to use curly braces. So if you want to make sure you never make a mistake, just use curly braces. Even if you just have one line of code in there, it will still work fine. And here's another where we have actually two expressions evaluated. If stopped and not enabled, do an axis stop and then wait. So it's going to check to see if stopped is true, and it's going to see if enabled is false. And if both conditions are met, it will output a true, and that if statement will execute those two lines of code. Pretty handy. An improvement on the if construction is the if-else construction. It executes one or more lines of code if an expression is true, and then it's got some alternative code that it can run if it's false. So it actually takes two possible paths here. One if it's true, one if it's false. Let's see that. All right, if h1 equals 100, go relative. Else, go relative with a different set of conditions. So if it's 100, it will do the first line, and if it's not 100, it will do the second line there. If h5 is greater than 10, change the variable in position to 1. However, if h5 is not greater than 10, then it's going to do another if statement after the else there. If h5 equals 10, set motor on to 0. Otherwise, if h5 isn't 10, set motor on to 1. So you can even chain these things together. You can build some very complicated decision-making structures. And again, of course, if you need multiple lines, then you've got to use curly braces. If h1 is greater than 100, go ABS and do a bit clear. And if h1 wasn't greater than 100, do these four lines of code. Set h1 to 0, do an axis stop, set re-enabled to 1, set motor on to 1. I think you get the idea. Now there's a trap here that I really want to sternly warn you about so you don't get your fingers caught in it. The single equal symbol and the double equal symbols mean two entirely different things. Remember, the single equal symbol is for assignment, assigning values to variables, copying one variable into another. The double equal is for evaluating whether something is equal to something. You cannot exchange these two things. They are totally different. It is very easy to use a single equal sign in an evaluation. The compiler will not complain when you compile your code, but your code will not run correctly. And let me explain why. It's going to do two very undesirable things. It's actually going to change a variable on you, and it will always evaluate to true whether it is or not. Let me show you. All right, here's our code. h1 equals 2. If h1 equals 5, then go 0. Otherwise, else, do a relative positioning operation. Now, notice we made a mistake. We should have had two equal signs there, but we only have one. Now, what will this do if we had written it correctly? All right, h1 is 2. So what's going to happen is it's not going to go 0 because it's not equal to 5. It's going to do the else code. It's going to do a relative motion. Now, what's really going to happen since we messed up here? Two things will happen. First, it's going to assign the number 5 into h1, so it's going to change h1 to 5. It thinks you're trying to do an assignment. So it's going to corrupt h1. Then it will automatically evaluate to true, and it will do go 0. So your code will do something totally mystifying just because you left one equal sign out. So don't do that. Be very careful. Let's do a practice activity. Let's make sure we really understand how if statements work. What we're going to do here is we're going to take this big kind of weird-looking block of code that does a whole bunch of ifs and elses, and we're going to figure out what actually executes and what doesn't. And we're going to do this based on the value of different variables. So let's do our first one here. We'll set h1 to 22, h5 to 12, h6 to 56, stop to 0, and status to that rather long hexadecimal number. All right? Now let's look at our code. Our first line is if h1 equals 100, so does h1 equal 100? No, it's 22. Now that's an AND statement there, and remember with an AND statement, every single thing has to be true or it evaluates to false. So it's definitely not going to execute the function code1. So let's go to the else. If h5 is greater than or equal to 6, is it? Yes. Now that's an OR statement, so if even one thing is true, it's going to evaluate true. So that means code 2 is what runs. That's what will happen here. All right, let's try another. Now, h1 is 100, and is stop false, not stop? Yes. So that means code 1 executes. Let's try a third here. h1 equals 42. Okay, so h1 is not 100. So that means we go on. Is h5 greater than or equal to 6? Nope, it's not. Is h6 less than 22? The answer is no, it's not. h6 is 100, so it's going to drop through to the else. So the first thing that's going to happen is code 3 and code 4 will run. However, we've got another if statement. Notice we're doing a bitwise AND operation. We're taking status and comparing it to a hexadecimal number. Okay, we're doing some bit testing here. So we need to work out the result of that. So, okay, this is what status is written in binary. It's in hexadecimal up there. I've expanded it out in binary here. Now here's our mask. That's hexadecimal 80 turned into bits. So what we're really looking at is this bit right here. We want to find out if that bit is 1 or 0. Well, of course, when we AND these two things together, we're going to get a 0. Therefore, it does not equal hexadecimal 80. Therefore, it will not run code 5. It will run, in fact, code 6. All right, be sure you understand that one. If you don't, maybe you want to pause, back up, watch it again. But we're going to do another one here just to be sure you've got it. Does h1 equal 100? Yes, it does, but stop is true, so it's not going to run code 1, so it drops through to the else. Is h5 greater than or equal to 6? Nope, it's not. Is h6 less than 22? No, it's not. That means that OR statement evaluates to false, so code 2 doesn't run. So we know, therefore, that code 3 and 4 will run because they're part of the else statement. But now we've got to again go through that status bit testing operation and see if code 5 or 6 runs. So again, let's take our status value and turn it back into binary. We'll take our mask. We're looking at this bit right here. Now, if you AND these two numbers together, we in fact do get this number back. We get hexadecimal 80. Therefore, code 5 will run. Hopefully that made sense. If it doesn't, I suggest you play this section over again. It's very important you understand these things. But if you're perfectly clear, let's move on. Now, one of the reasons we use things like if statements in programs is to decide what to do. What sequence of operations do we want to do? Remember, IPOS programs are to make motion. They make different kinds of motion take place. So most motion applications have what's called an operation list. It's a group of actions that the system can take based upon some inputs. For example, this is a typical operation list. It lists different things that will happen, and it's using 3 bits, bits 0, 1, and 2, to indicate which action we want to do. So we're sending a 3-bit number in from, say, the digital inputs, and based on those numbers, we decide what to do. So if all 3 bits come in 0, we idle. If bit 0 is a 1 and the other 2 are 0, we turn clockwise. If bit 1 is a 1 and all the others are 0, we turn counterclockwise. If bits 0 and 1 are 1 and bit 2 is 0, we go to the home position. And if bit 2 is set to a 1 and the other 2 are off, we go into auto operation. And then the other 3 combinations are also idles. So there's actually 4 different idle states here and 4 actual operations. Okay, this is an operation list. If you've played with MoviDrive B application modules, you know that a number of them work this way, where you send in bit patterns for specific operations. So let's assume that the operation is being specified by 3 digital inputs, DI 13, 14, and 15. And we access these through H520, which is also called input level B. That's its alias name. And so what we do is we mask off the bits we care about, 13, 14, and 15, and we extract them. So here are the bits we care about in 520. We apply a mask like this with an AND operation. We use the bitwise AND operation. And then finally, after we do that, we shift it 11 times to the right. So we shove those bits down to the least significant bit end. And what will be in H1 after we do this is a number from 0 to 7. And that number corresponds to these rows in the operation list. And as you can guess now, we're going to use an if statement to decide what to do. So we now need to test H1 and do the different decision paths. And we can do this in several ways, but a simple way is to use a series of if-else statements nested inside each other. So if H1 equals 1, call the function move clockwise, else. If H1 is 2, move counterclockwise, else. If H1 is 3, go to the home position, else. If it's 4, do auto. And then, what about everything else? Well, there's a nice, easy way to do that. Just have one final else. Call this the everything else condition. If else, idle, because every other mode was idle. Always handle that everything else condition. Never let your code just drop through into the unknown. Now, once you've gone through a properly constructed if-else sequence, execution continues on the line after the end of the sequence. So every one of these, once it's done its function, comes out here, and code continues from this point on. So, time for a hands-on task. We're going to start a new program, program 5, so create a new source file, and here's what you're going to do. You're going to use input level B as well as the wait input function to read the inputs, and I'll leave it up to you to figure out where each one's appropriate. I want you to turn off all the digital outputs 10 through 17, so all the lights are off. Do nothing until DI 10 through DI 17 are all off. So make sure all of these are off. and then wait for a change in DI10 through DI17. Now, if DI10 is turned on, flash this sequence. So turn on every other light, then alternate to the other lights, then go back to every other light. So flash that sequence, those 3 patterns of lights. If DI11 is on, flash sequence number 2 instead. DI12 is on, flash sequence number 3. And if any other pattern is present, flash the error sequence, which is a full row on, a full row off, a full row on. Pause half a second, 500 milliseconds between each light pattern. And when it's complete, turn all the lights off. And then wait until DI10 through 17 are all off again, and then start all over again. And use only the structures and functions we've discussed so far. Don't branch off and do anything different yet. All right, pause the video, give it a try. All right, let's see how you did. Let's take a look at your code and see how it compares to mine. All right, well, we're ready to write a program. We've got a number of conditions we have to fulfill, so we're going to work through these just one by one and take care of them, and you can see how I handle it, and hopefully you did something similar. But if whatever you did worked fine, then of course that's great. Now, the very first thing we have to do is make sure all the lights are off from DO10 through DO17. We're using those lights, so we want to make sure they're all turned off. And of course, that's easy. We can just write to opt-out-p-IPOS and put a 0 in there, and that'll shut everything off. We've done that before. So we're going to do everything inside our while loop here. There's really no initialization we have to do. Everything is just inside the endless loop that's really the body of the main program. Okay, so there we go. By setting opt-out-p-IPOS to 0, we turn off DO10 through DO17. The next thing we need to do is we need to look at the switches that are controlling our program to decide what's going to happen. We are not using the switches connected to the regular built-in I/O, in other words, DI00 through DI07. We're using the switches connected to the expansion card, DI10 through DI17. The first thing we have to do is just make sure all the switches are off. We're not allowed to do anything if the switches are on. You might be thinking, well, that's easy. We'll just use wait input, and we'll set the first parameter to 0, making it wait for a 0, and then have it monitor DI10 through DI17. But here's a problem. Wait input is basically a giant OR operation. In other words, if any one of its conditions is fulfilled, it'll stop waiting. That means if at least one of those switches is off, the wait will end. But we really want an AND operation where we say every single switch DI10 through DI17 is off before we can continue. So we really can't use wait input for this. We have to do something totally different. Here's what we're going to do. We're going to have an if statement where we look at the individual bits associated with those IOs and make sure they're all off. Now you're saying, where do we do that? Well, remember I told you there is a system variable called INP level B, which actually reflects the status of every single input, including the built-in ones. So it's got 16 bits near the bottom half of that word that reflect DI00 through DI17. Now, we're not interested in the first 8 because we're ignoring the built-in I/O, but we are definitely interested in the second 8. Here's kind of what we're going to have to do. We're going to have to take that word, we're going to have to mask off the bits of interest, and then work with them. So here's what we're going to start off doing. First of all, we're going to put in an if statement here. And we're going to put what we're checking in parentheses, and we're going to say this. We're going to say if INP level B ANDed with a mask, and we're going to mask off some bits. We're going to mask off the ones we don't want and let through the ones we do want. So this is going to take 16 binary digits here to set this up. So I'm going to put a 0B here, and we're going to do this in binary just so you can see the bits. Now what I want is I want all the option input bits to come through. So I'm going to type in 8 ones. And I want to block off the bits coming from the built-in I/O. So I'm going to put zeros for the bottom. So I'm blocking off the bottom 8. I'm letting the top 8 through. What this is going to do is it's going to give me just the bits I'm interested in. Now I'm going to do something else just to make my life easier. I'm going to shift to the right 8 times. What this is going to do is take the bits that I'm interested in, shove them down so they're down at the bottom now. So I don't have to worry about those bits all being up at the top. That's what I've done here. So I've masked it and I've shifted it. Now what I want to check is I want to see if these bits are equal to 0. So I use a double equal, remember, never single equal in an if statement. And if they equal 0, and I need to get my parentheses matched up, so I need one more parenthesis here. I've got 3 left-facing parentheses and 3 right, so that's good. So here's what I'm doing here. I'm basically saying that if those 8 bits that I have shifted down all are 0, in other words, my whole number is 0, that means every single thing is off. If even one switch is on, then this is not going to be 0. All right, and so I'm going to have my if statement. And then once that condition's fulfilled, I can move on. I want to pause here and make a suggestion. You're going to have to do this a number of times as we're looking for the different bits that are going to trigger different things happening. Do you really want to type this or cut and paste this long line with the masking and shifting over and over again? The answer is no. Unless you're a glutton for punishment, I very much doubt you want to do that. What I'm going to do instead is I'm going to create a constant, and I'm going to associate it with this expression here, and I'm going to use that constant in its place, and that's going to make my code more compact. Here's what I'm going to do. I'm going to create a pound define, and I'm going to call it inputs, all uppercase, and it's going to have that expression in there. And I'm going to just use inputs whenever I want to access my inputs. I'm going to get rid of this if statement here, and I'm going to instead do this. There we go. If inputs equals 0, remember double equal, and that'll see if DI10 through DI17 are all off. And if they are, then it's okay to continue. If they're not, we're just going to keep looping in that while loop until all the switches are off. All right, that took a little while to explain, but I'm just showing you how to work with the inputs and also how to do it in a slightly cleaner way than having to type all that code over and over and over again, just by using a constant. Okay, so that's our first step. Of course, our if statement now needs some curly braces, so I'm going to indent, put our open curly brace, and then we're going to have all the code underneath that. So once the switches are off, we'll go into this if statement. Now the next thing we have to do is wait for one or more of DI10 through DI17 to go on. Here we can use wait input because that's just fine. Remember, it kind of does an OR operation. If it sees any one of those bits go on, it'll be happy. So I'm going to put in this piece of code here. It's just going to do a wait input. It's looking for a 1, and it's going to look at those top 8 bits, DI10 through DI17. It's going to ignore the built-in ones, DI00 through DI05. Remember, it doesn't look at the top 2, 6, and 7. So it's going to ignore those. It's just going to sit here and wait. And if one or more switches goes on, then it's going to exit the wait, and the next thing will happen. Now, we have to decide, what do we do after that? Well, remember, here's what we have to do. If DI10 goes on, we flash one light pattern. If DI11 goes on, we flash a second pattern. If DI12 goes on, we flash a third pattern. And if anything else goes on, we flash an error pattern. And our light patterns are different for each of these. We're just going to be manipulating opt-out IPOS to do those, and we're also supposed to pause a total of 500 milliseconds between patterns. All right, so now I'm going to really whip through this. I'm going to put all the code in that does that, and I'll just briefly go through it with you to make sure you understand it, but this is really simple code here. All right. Let's just look at this quickly. Notice I'm using my inputs constant, and I'm using binary. I'm saying if the input equals a 1 in the lowest position, that's DI10, then flash this pattern. So I set opt-out PIPOS to the first light pattern. I do a wait to a constant delay. I output the second part of the pattern. I wait again. I do the third part. I wait again. If it's not that one, we have an else statement, and we say, okay, if it wasn't a 1 in the lowest position, is it a 1 in the second lowest position? So we do another if. That would be DI11. So that's our second pattern, and here's our flash pattern for that. Okay, if it's not that, else, if it's in the third position, is it DI12? If so, flash that. And finally, our last else, if it's not that, well, it's one of the errors, so we flash the error pattern. And that is it. Yeah, it's a lot of code, but it's really simple code. Now, you notice for wait, I'm using a constant called delay. I'm supposed to do 500 milliseconds. You may wonder, well, why didn't you put 500 in there? The answer is that's a lot of delays. What if I decide I want to change it to, say, 750? Do I want to go and replace all those waits? No, I want to create a constant that I can just change here. I'm going to be smart, and I'm going to go up here and do a pound define, delay, and define it to 500 milliseconds. Okay. And I'll make a comment here because I'm a good programmer who documents his code. I'll just say delay time in milliseconds. Now, the last thing I have to do is make sure that I've got all my curly braces matched up and that I don't have any mismatched ones. So I'm going to look at this one for the original if and kind of zip down here and make sure we have a closing one. And we don't, so I better close that guy up. And I think everything is now correct. Of course, if I've got a mismatched curly brace, I'm going to get an error when I compile. But I think we're good here. So let's just go up here, do a compile, and uh-oh, I do have a problem. So what's my problem? Okay, I paused and I took a look at my code and I realized I was missing one curly bracket right there. That can happen. It took a while to find that because the error didn't really tell me I was messed up. It just gave me kind of a cryptic error message. So that happens. Again, always just check your curly braces, make sure they match up. So let's compile this again and just confirm that it's good, and it is. Now we're happy. We're going to go ahead and run this and test our program. You can see if everything works. So let's start it up and go flip a few switches. All right, as you can see, I tested every possibility. I checked the 3 switches that are supposed to give specific patterns. They work. But I also checked the other switches that were all supposed to flash the error pattern, and that worked as well. Remember, when you're testing programs, always test all the possibilities to make sure you've covered your bases. All right, well, that is it. This program works, so that's cheering. And hopefully this made sense to you and that your program worked somewhat similarly. As you can guess, there's a much cooler way to do what we've just done. Nested if-else statements do the job, but they're a little bit clunky, especially if you have a big decision structure with a lot of possibilities. So let me show you an alternative that I think you'll like better. All right, this alternative is called the switch case statement, and it's kind of an interesting approach. It's a little better and more elegant than nested if-else statements. It is a little bit quirky, it's got some odd limitations, but it's still pretty usable. Here it is. As you can see, it begins with the statement switch, and then the variable you're checking in parentheses, and finally a set of curly braces. These will contain all the remainder of the code. And then inside these, you'll have a series of case statements. You can see case here, and it's got the number after it. That's one of the possibilities, one of the possible values H could be. There's a colon there, notice that's kind of unusual. And then after that, one or more lines of code to execute if that particular case is true. So this is sort of like a single if statement in here. And of course, then you'll have as many cases as are necessary to cover all the possibilities. By the way, you do not have to use curly braces underneath the cases if you have more than one line of code. This is kind of an exception to the usual curly brace rule. Of course, the switch statement has curly braces enclosing everything, but the individual cases don't. And then, this is very important, after the code that goes with the case, you have to have a statement called break, which ends in a semicolon. And what that tells it to do is exit the whole switch structure and resume after the bottom curly brace. So here is a complete switch case structure. You can see it's got 4 cases, case 1, 2, 3, and 4. And each one has code going with it. And you can see I'm implementing that operation list that we talked about a few minutes ago. One other thing I would like to mention, just as an aside, the values that go after the case statements, like the 1, 2, 3, 4, those must be constants. They can't be variables. They can either be numbers like you see here, or they can be named constants that you've created with the #define statement. Now, there's one other little thing to be aware of here. It is always smart to have an everything else condition, and the way you do that with this structure is you put, instead of case, the word default, colon, and then after that, code to handle the everything else. So default comes last, and it handles the everything else condition, which in this case is the idle state. And that break is optional for the default statement, but I think it's a very good habit just to put breaks at the end of every single part of the case structure, because if you don't, you can get yourself in trouble. There are a few interesting nuances to using switch case, and here's one that's kind of neat. If you have several different cases that have the same code, the same action sequence, you can group them together like this. So for example, if case 0, 3, and 5 do exactly the same thing, just put them one after the other and then put the code to go with them. And if cases 1, 2, and 4 have another common action, then put that together with the code after it. And 6 and 7, you can do that. So this is kind of interesting. This is almost like using an OR within an if statement, where you're combining several expressions, and if any of them happen to be true, then it will carry out the same action. So that's kind of a useful nuance, I would say. And by the way, you don't have to use a default line if you don't want. Notice in this case I don't. That's because I've covered every single possibility, so there are no everything else's. But it's still smart if you aren't sure to not let the code just fall off the bottom. All right, now, one thing to think about, beware another trap. We don't want to get caught in this one. Forget the break statements at your peril. If you forget a break statement at the end of each case, you could have some very weird things happen. For example, look at this code. Notice I have left the breaks out from every single possibility. All right, what's going to happen? Well, let's say if h1 equals 1, so it's the very first case, guess what will happen? It will move clockwise, and then it will move counterclockwise, and then it will go home, and then it will go auto, and then it will go idle. Every single line in the switch statement will execute. The break is there to tell it to get out of the whole switch case structure. And if you forget it, it will just start running through whatever cases remain and executing every single one. That is not good. So don't forget the breaks. All right, hands-on task ahead. We're going to create a new program, program 6. So you're going to make a copy of program 5 and use it as program 6. And here's what I want you to do. This is pretty easy, actually. Just rewrite program 5 to get rid of those nested if-else statements and use the switch case structure instead. So this is really just improve program 5 using what you've just learned. Call it program 6. Shouldn't take you long. So go ahead and pause the video and do it, and we'll come back and see how you did. All right, let's see how you did. We'll take a look at my code and you can compare it to yours. What we're going to do here is simply take program 5 and change it to use the switch case construction instead of nested if-elses. Now what I've done here is I've taken program 5, I've saved it as program 6, I've changed my header, and I've deleted a lot of the code, although I've kept some of it. Of course, you probably didn't do that. You probably just changed it and did some reformatting, but you don't really want to watch me spend most of my time reformatting text. So instead, what I'm going to do is cut and paste the new code in, but you've noticed I preserved some of the old code. Let's see what we have here. Notice that I have kept my inputs constant, my delay constant. Of course, I have my main while loop. I have my opt out IPOS set to 0, and then I have my if inputs equals 0, which of course you remember checks for DI 10 through 17 being all off at once. And then that wait input, which spots when any one of those switches goes on. That's all I've got here. Everything else is going to be new code. We're going to do this pretty fast because I don't think this is terribly complicated. Our main goal is to replace all those if statements with a switch construction. So I'm going to type in switch and I'm going to put in inputs because that's what we're watching. And I'm going to put an open and a closed curly brace so we don't have mismatched curly braces. And then I'm going to set up all my cases. So my first case is going to be the situation where the bottom 1 bit is on. That's this one. Don't forget the colon, by the way, at the end of every case. That's an easy thing to forget. And I'm going to do something else as I type these. I'm going to type the break in right away just so I never forget those, because remember, forgetting a break is a very bad thing. All right, here's my next case. This is going to be DI 11 being on, so that is the second to the bottom bit being on. And again, another break. And then DI 12, which is the third bit on. So these are my 3 situations where I'll get those 3 unique light patterns, and of course everything else is going to be an error. So I'm going to use the default final condition for that. And of course you don't have to have a break for default since it's the last, but I think it's a very good habit just so you don't get in the habit of forgetting breaks. Okay, so this is my switch construction. Now all I've got to do is put in those light patterns and their delays. So I'm going to do a fast cut and paste with this, and then we'll test it out. And that's it. You can see we've got our flash patterns. This is the same code we had before, nothing fancy here. We have our weights using the delay constant. And I believe I've got all my curly braces matched up, so let's go ahead and just compile this. And it compiles fine. And we'll run it. And I'm going to test it again, and I'm not going to show you this time because if it works, it's going to do exactly what you've just seen a couple minutes ago. So let me just confirm it works, and then if it does, I'll tell you and we'll be done. Okay, well that definitely worked. All the blink patterns worked, including all the error possibilities, and so we've confirmed that everything is running fine. You can see that the switch case construction is a lot more elegant than the if-else. It's a little more readable, and I think in many ways it's just the optimal thing when you've got to do a lot of comparisons with different actions. One final little handy thing I want to mention, and then we're done. You've been including that file iob.h in all your programs, and here's something it does for you. It's defined a whole bunch of aliases for all the digital inputs, DI00 through DI17. You can see the actual code that's in there, and you can see it's using bitwise operations to mask off the bit of interest. This is really helpful if you just want to check one of the digital inputs to see if it's true or false. You can just do this. If DI10, and if DI10 is true, that if will execute, or if not, DI00. And if it's false, then that will execute. So you can just do that very quickly using this handy little shortcut if you just want to check an individual digital input. IOB.h also defines the digital outputs. Now you can't alter these. This is to read what their current state is. Remember, there is a memory location, a system variable, H521, which lets you know the status of all the digital outputs, both the built-in ones and any on the option cards, and that's available too. So by all means, use that. This is a useful feature. Take advantage of it. And that is it. That is the end of session 7. We have just one more session where we're learning the IPOS programming language, and then we're basically at the midpoint of our class, and then we'll move on and take a look at motion control. So that's it. See you later.